Okay, let's start. Well, it is a great pleasure to me to introduce Andressa Cerqueira from Federal University of San Carlos. And today she will speak about the Spatial Gibbs random graphs. Thanks, Andressa.
Thank you, Manuel. It's a pleasure for me to be here. I would like to first thank you the invitation. It's my first time in Chile, even virtual. I hope to visit Chile in person someday. Okay, so let's start. Today, I will talk a little about spatial Gibbs random graphs. And in this talk, I would like to compare some results that we have in this field and explain some kind of techniques that we can use that I think that is also useful for different problems. So this is my goal with this talk. So to start, since we are going to talk about random graphs, I would like to give some motivation about what we are interested to look at this. So here, suppose that I have the vertices of the graph that represent some kind of objects that we are interested in. So here, the vertices of the graph represent airports. And then we are going to connect vertices of the graph in such a way that we are going to represent some kind of interaction between the vertices. So here, the edge represents that I have a flight between two airports. So I hope you guys can recognize what is this plot here. Is the Brazilian map. So here is the airports from Brazil. So when we have this kind of data, we can think about analyze this kind of data or have some kind of questions that we want to answer from two different points of view. So the first point of view is a statistical point of view, where we can define a statistical model. Then we can try to infer the parameters of this model. If this model is a parametric model, we can test hypotheses about this network using statistics, or we can also think about cluster nodes of the graph in different communities or regions. From probabilistic point of view, we can define a probabilistic model and then study some kind of properties of this model in the graph. So what happens, for example, when I have the number of nodes going to infinity? So what happened with the graph? Actually, let me just come back here. Actually, I'm just here in the middle, right? So sometimes I do some probability, sometimes I do theoretical statistics. I like to do theoretical statistics and also probability. So since it's a probability seminar, I will talk about a work that's more from the probabilistic point of view. But if you guys would like to check, I'm also working with clustering nodes of the graph. So proving consistency of estimators, this kind of stuff. But okay, let's talk about probability here. So, okay, so first I would like to introduce a model. I don't know if you guys have heard about this model before. It's called exponential random graph model. So for this kind of model, we are going to represent the graph by its adjacency matrix, where each entry of the matrix is given by 1 if I have an edge between pair of vertices and 0 otherwise. For the exponential random graph model, we are going to define the probability of observe undirected graph with this probability here, where here theta will be the vector of parameters and S of X will be a vector of statistics that we are interested to look at the graph. So this model is vastly used to analyze social networks because we can use this model to represent some kind of structures that we can have in the graph or that we think that's more likely to have in the graph. So for example, we can think about S like a statistics that is going to count how many edges I have in the graph. Or if I have a different structure, I can count how many stars. So how many of this configuration, this is called 2 star. So how many of this configuration I have in the graph, or how many triangles I have in the graph. Why this is interesting? Because, for example, if you're analyzing a social network, this kind of structure here have the how can I say, the power to analyze transitivity in the network. For example, I have here 3 people. So this one is friend of this one is friend of this one. So we can think that's more likely to have a connection between those 2 people here. So we can use these counts to analyze some structures in the network. So this model is well known. They have a lot of, there are a lot of papers how to estimate theta from a statistical point of view, how to sample this method from a probabilistic point of view, and also some kind of typical configurations that we can have in this, using this model when n goes to infinity. So when the number of nodes go into infinity. So when we use this kind of model as a motivation, and I go back to this example here, we can think that when I have these kinds of network, you can think that to have a flight from the south to the north of Brazil, we can think that maybe it's more likely to go to the center, so go to the capital, and then go to the north. So you can see that here, I'm pretty sure that here is the capital, so here is the Distrito Federal. So you can see that we have a lot of connections going out from this point here. So we can think that it's more likely to have a connection between vertices that are close. So I don't want to put an edge here for edges that are very far away, but maybe I make a path going to a vertex that's close to this one and then going to the other. So this is the idea that we are going to explore here. It's have a model that describe a balance between the structure that we have in the graph and also the distance between the vertices. So this is what I'm going to introduce as Spatial, because we're now going to take in account distances and Gibbs random graphs, because I'm going to define a Gibbs measure, as we can see that we have here. Statisticians will call this like a exponential family distribution, but for people from probability, look at this like some kind of Gibbs measure. So I will concentrate this talk in 2 papers. So the first one from Pablo Ferrari, Percheski, Cisco, and Anatoly Amberstaff. They study this kind of model, the Spatial Gibbs random graphs. And the second paper, it's a collaboration with Professor Nancy Garcia that I have worked with from University of Campinas. So I'm going to make a kind of comparison with what kind of results we have in both papers. So let's define what we want to study. So since I would like to take in account distance between vertices, I would like that the set of vertices is located in some kind of metric space, some metric space. So here I'm going to consider Z2. So suppose that we have a finite set of vertices in Z2. Here's just like all possible graphs that's undirected. So I don't have direction between in the edges. So this is just the all possible graphs that I have with this finite set of vertices. And then I need to define some kind of distance, the distance between vertices. So this distance here, I will say that I have a vertex I and j, and I will define how is the length of vertex I and j. This is just the distance between I and j. And here I will just use the L1 distance. Yeah, okay. So this is what we call the length of the edge. I know that I will talk a lot about short and long edges. So you think that short edge just have a small length, and long edge a bigger length L. All right, so now let's define the model. So for fixed parameter, positive parameter beta, we are going to define the finite volume Gibbs measure. So here I have a finite set of vertices V, and I will define this measure. So this measure is quite similar with the exponential random graph model, but now I will take in account the distance, the length of the edge. So here, the first term of my Hamiltonian will count how many edges I have in the graph, and it's going to weight this edge by its length. So basically, when I use this Hamiltonian, what I'm going to do is penalizing long edges in the graph. So I prefer to have short edges in the graph. We are also going to use and define a function f(v) of x that will take in account extra terms that I have in the graph. For example, count triangles, count stars, or whatever you want. But I need some conditions for this function. These conditions I'm going to say right now. What is this condition? Then we are going to see some examples of functions that satisfies these conditions, just to make sure that's not like crazy conditions that we don't have any function that satisfies it. So first, I would like to define two graphs. It's simple. Imagine that you have a graph X. Then we are going to take a pair of vertices I and J. The graph I and J1 is just the graph when I have this edge in the graph. And the graph X I J0 is just when I remove this edge from the graph. So what I'm going to do is trying to compare what happens when I just change one edge in the graph, because this is the dynamics that I'm going to define in my graphs. So we are going to consider functions f that satisfies first, when I look at this difference, so when I compute the f function for the graph with the edge I and j, and when I compute the f function in the graph without the edge I and j, this difference here will only depend on edges that are connected to vertex I or connected to vertex A. The second thing is just that I can have a lower bound n, that's a constant, greater than -1, to this difference of functions for all pair of vertices that I'm going to take in the graph for all possible graphs. So I have this lower bound here. So let's see some examples of functions that satisfy these conditions here. And then we can think about models that we are going to consider. So the first model is the model of in this work. So in this work, the authors use the same kind of measure. So just to make clear that my Hamiltonian will always have this part that will penalize long edges plus some function. And the function that they are going to use is this function here. So what's this function? This is the sum over all vertices in the graph of this phi function. And what is this phi function? This is a function that's equal to a constant, to a positive constant, when the degree of node I is equal to 0. So degree is just how many edges are connected to this vertex. This function is equal to 0 when the degree of node I of the graph is equal to 1. And this function here is proportional to the degree of node I when the degree of node I is greater than 2. So when you use this kind of function, what we are going to do? So the first part of the Hamiltonian will penalize long edges. And this function here will penalize edges with degree 0 or degree greater than 2. So what we want to expect to have is a graph with short edges and with degree around 1. So this is the model. So let's check if this model satisfies the conditions that I have shown before. So first, we need to look at this difference. So this difference here is just look at the phi difference, the difference of the phi functions for node I and the difference of phi functions for node j. So let's check what's the first part here when I look at the difference of phi function for node I. So this is, I'm not going into details how to have this, but here, when you look at this difference, if you look here, this difference will only depend on degree of node I. That means that this difference here will depend only on edge connected to I. This will be the same thing when I analyze this difference for node J. So for node J, here we are going to have all the degree of node J. So this difference will only depend on connections on edge that's connected to node J. So this difference here will only depend on edges that are connected to node I or J. So this is our first assumption. This is just to restrict the edge that I need to look at the graph. This difference just say to me that to compute this, just look at the edges that are connected to I or J. So you just restrict the number of vertices that you need to look at the graph to compute this difference here. And the lower bound here, so for this difference here, the lower bound is given by minus e to 0. So using the sum here, the lower bound m is given by minus 2h0. So both conditions are satisfied for this model. The second model is a model when I'm going to have this Hamiltonian for the first part is I'm just counting how many edges I have. And the second part that will be my function f is the number, I'm counting the number of stars and penalizing by the length of the edges. So what we have here, let's see what happens to this difference here. So suppose that I and j is, let me put this here because I can see. Okay, so suppose that I and j here is 1 and 3. So we are looking at this red edge here. So when I look the number of stars when I have this edge, so I have the star 1, 3, 6, and 3, 1, 4, right? And we have more stars here, 4, 5, 6, 5, 6, 2. So now suppose that I remove this red line. I remove this red edge here. So now I don't have anymore the star 1, 3, 6. And I don't have anymore the star 3, 1, 4. But the other stars remain in the graph. So basically, this difference here will only depend on edges that are connected to 3 and edges that are connected to 1. So this is just a picture to explain, but we can write this. So here, this difference will only depend on vertices that are connected to I, and will only depend on vertices that's connected to J. So the first assumption holds. And the lower bound for this difference here is just when I have the empty graph. So when I have the empty graph, I don't have stars, and then m is equal to 0. So we also have the lower bound. So this is just an example how kind of models we would like to analyze. When we think here about, instead of 2 stars, we think about triangles, for example, it's the same thing. M is also 0 when we have the same, that this difference only depends on vertices connected to I or J. Okay, so this is the model. And now I need to introduce the question, what we are interested to look at this model. So we can define this model when V is finite. But our goal is to study what happens when V is, for example, our entire space, Z2, or when V is an infinite set of vertices. So we would like to study if there is or there is not an infinite volume Gibbs distribution that I'm going to denote by me. So this is our goal. And then also study some kind of properties of this measure. Okay. So in this paper, the authors consider functions like this. Remember these 5 functions that just consider the degree of the nodes. What they prove in this paper is that the infinite measure mi can be constructed as a limit along the finite sequence. So if I take the measure mi of v and then just make, for example, I can take not balls, but we can take squares in Z2, make these squares to infinitive, then we can construct this measure mi. And what is interesting here is that, okay, suppose that we have an infinite measure. So we have an infinite number of vertices. What we can think, So we can think that we can have a vertex connected to infinite number of vertices, right? But what's interesting here is that the authors prove that actually this measure me, the infinite measure, is concentrated on the set of all graphs with finite degree. So we can guarantee that here all the vertices have a finite degree. Why is that? So we can think by intuition that we are penalizing long edges. So we can think that one node is connected to vertices that's close to this one and not with vertices that's far away from this one. And also in this model, they are also penalizing degree greater than 2. So we can expect to have this measure concentrated on this set. Okay, but here they did not discuss anything about uniqueness of this measure, and this is our contribution, and a little more contribution. So in this paper here, first, we are going to define a function, alpha of beta. This function here will only depend on the beta and the lower bound m. So here is where I'm controlling the functions f that I'm going to use. So here's the lower bound. We are going to define a beta critical, so this beta star, that's the minimum value of beta such that alpha of beta is smaller than 1. So when we have a model for which a model defined for betas greater than this beta star, I can guarantee now the uniqueness of the infinite measure. And we have the same kind of result that this measure me is also concentrated in this set of graphs. Okay, so this is the results that I'm going to talk today. So I'm going now to give some ideas how do you have the uniqueness. So the idea to have the uniqueness here is using a technique that Brazilians really like to use, that's to construct a perfect simulation algorithm in such a way that I know that I can sample from this infinite distribution me. So if I can construct a way to obtain this measure me, then of course it exists and its uniqueness is unique. So this is the technique that I'm going to talk now, how to do this. So first, let's see how we can construct the measure me v when v the set of vertices is finite. So what we are going to do is just to, when v is finite, we are going to define a Markov process on the set of graphs in such a way. At each time, I'm going to remove an edge in the graph, or I'm going to add an edge in the graph. Okay, so to add an edge in the graph, what I'm going to do? Suppose that I have a graph, and then the edge I and j will try to born in the graph. I was playing with that. So this edge will try to born in the graph with this rate. So this rate here will depend on the length of the edge and also in this lower bound n. So what happens here? The edge I and j will say, hey, I would like to be adding the graph. But I will say, no, we will only be adding the graph with this probability here that will depend on the current configuration that I have in the graph. So this probability here to add this edge in the graph is given by the difference between the f functions and also the lower bound here. So what's important here is that since it just depends on this difference, remember that my first assumption says that this difference here only depends on edges that are connected to I or j. So this probability here will only depend on edges that's connected to I or j. We are going to use this later. So just want to emphasize here why this assumption is important. And to remove edges, we are just removing edges with rate 1. When we don't care if you want to be removed, we just remove. Okay. So when v is finite, by this construction, the invariant measure of this process is just the measure that we are interested to study. It's me of v. Okay, so the technique that I'm going to present is how to construct this measure in the finite volume when V is finite, and also when we have an infinite number of vertices, using a graphical representation of this process. So this is not a new method or technique. It was used before for loss networks, for easy models, or interact point process in these works here. So I'm just using this technique to see what happens in graphs when I have dynamics in graphs now. Okay, so let me explain what's this graphical representation. So here's me. This is, I was trying to represent this, what I have in my mind by this picture. So here I have vertex I, J, and K, and we are going to look at the edge I and J and JK. So at each pair of vertices, we are going to associate a Poisson process with height. That's the rate that I defined before, is the rate that the edge will try to be born in the graph. And then I will just order the occurrence times of this process. So here is the first time that vertex I and J try to be added in the graph, the second time, third time, so on. So here it's not intuitive, but imagine that 0 is here, and then we are growing like this to the positive. Here is not negative, okay? And the same thing for J and K. So this is the first time that this edge tried to be born in the graph, and so on. So to each time that the edge tried to be born in the graph, we are going to associate a exponential distributed random variable with mean 1 that will give the survival time of this edge. So that means that the edge will try to be born at this time, and it will survive for S, I, and J units of time. The same thing for this time that he tried to born, the same thing here, and here for J and K. So this is like just how long this edge survives. All right, what else? So now, if you look at this representation here, we can see these rectangles here. So basically what we are going to define here is what is a rectangle to us. So a rectangle to us, it's like these rectangles, but we are going to define the basis of this rectangle by the edge I and J that we are analyzing. The birth time of this rectangle is the time that it tried to born in the graph. The death time, it was the time it survived plus the survival time. And the lifetime is just this length of this rectangle. I don't know if we say length or height for rectangles, but it's just this time interval here. This is the lifetime of this rectangle. So it dies here, and then we have other rectangle here. So we can now define a random family of rectangles. Since T and S are random variables, we have this random family here. So now we are going to deal with rectangles using this representation. Okay, this is just to say that RST, so if I fix a time interval ST here, I have this RST is all rectangles that was born in this time interval. Okay, so let's see how we construct the measure, the Markov process that I defined before when V is finite. So when V is finite, we can define the set of all rectangles that was born in the time interval 0t. So fix here some time. And I'm going to look at all the rectangles that was born here. Since V is finite, we can order all the occurrence times that we have. So I can have a mark that can be a birth time or a mark that can be a death time. So we just order all the marks. Since V is finite, we can do this. V is finite and the time interval is also finite, we can do this. Okay, so let's see what is the dynamics that we are going to do. So suppose that we are going to look at this mark, Rm. So Rm is here, it's this mark. this is the birth time of this blue rectangle here. So since this Rm is a birth time, what we are going to do, we need to check if we are going to add or not this edge in the graph, right? So we are going to add this edge in the graph with the probability Q that I defined before. And remember that that probability only depends on edges that are connected to J and K in this case. So what I need to do is just look at the set of all rectangles that was born before this one, such that the bases intersect J and K. So K belongs to the bases of those rectangles and J belongs to the base of those rectangles. Like, for example, if we look at these red rectangles. So we need to look at all these rectangles to decide if we are going to add this edge in the graph or not. Okay, but when Rm is a depth mark, so in this case, this is the depth mark of this rectangle again, we just remove this edge from the graph, okay? Okay, so this is the dynamics. So we can do this when V is finite, as I said, because we can order the marks. But when V is infinite, we cannot do this. We cannot do this construction. But there is something important here in the finite construction, because as I said, when R, let me just come back to the picture, when R is a birth time, that means that to decide if I'm going to add this graph, this edge in the graph, I just need to look to all rectangles that was born before, such that J belongs to the basis of this triangle, this rectangle, and K belongs to the basis of this rectangle. This is the rectangle that we need to look. So here, when V is infinite, what we can try to do is write this relation here to decide if an edge I and J will belong or not to the graph. So as I said, when I have an edge I and J, what I need to look? First, I need to look all the rectangles such that I have intersection in the base, such that I belongs to the base of this rectangle and J belongs to the basis of this rectangle. This is because of my assumption that the difference of the f functions only depends on edges that are connected to I and J. This is why the function is important, that assumption. We need to look we need to look all the rectangles that was born before rectangle R. So by this picture here, if I would like to decide if I have an edge at this time, I need to look all the rectangles that was born before. And also I need to look at of all the rectangles that is alive at this time interval. So for example, let me see, this rectangle in red is not alive. Oh, sorry, let me come back here. So here's the birth time of this blue one. So this red is not alive anymore. So it doesn't matter, we don't need to look at this rectangle. So using these three conditions here, we can define what we call, what the authors was of that paper that I have shown has used before, what's called clan of ancestors. It's just like I'm looking at the ancestors of such rectangle. So I fix a rectangle with bases I and J, and I'm going to look all the ancestors of this rectangle. So this is the idea. So when V is infinite, we can do this, right? Just need to go back in time and see all the ancestors that I have. All right, so just to define what's ancestor here, it's just like here I define ancestor for each vertex, but we can define ancestors for rectangles or we can define ancestors for edges, doesn't matter, but I will define here for vertices. So to define the ancestor of vertex I is just the set of all rectangles such that I belongs to the basis of this rectangle and its rectangle is alive at time t. To define the second generation, what I'm going to do, just define the first generation for all rectangles that are in the set. To define the third generation, I will define the first generation of all rectangles that belongs to the second generation. And then I'm just going back, define all the ancestors that I have for this rectangle. So here's how we define the generation n. As I said before, just define first generation of this of the set that I have before. And at the end, I can define what's the clan of ancestors. This is just the union of all generation of ancestors. So this is the clan of vertex I. So now is our result for clan of ancestors. Let me put this again to the side to read. So these results say that if with probability 1, all vertices I belongs to V, so V here can be finite, so V here can be Z2, for example. So if all vertices of the graph have not an infinite number of ancestors, so it just have a finite number of ancestors, then we can construct the Markov process in the real line in such a way that the measure V is the invariant measure of this process. So when V is Z2, I can just have that my infinite volume Gibbs distribution is the invariant measure of this process. So what's important here? It's important that in some point, I don't need to look anymore to the past. I don't need to look to more ancestors, otherwise they will never end. So, okay, so what is result that's important? So what's important here is that first, when I have, remember that I defined before this alpha of beta function, and when I have this alpha of beta is smaller than 1, I guarantee that all the vertices of the graph have not an infinite number of vertices of ancestors. So all the vertices have a finite number of ancestors. So you can imagine, because of this condition here, that to have that, we just dominate the clan of ancestor process by a branching process. And then here just guarantee that we have the extinction of the branching process. So we have that we don't need to have more and more ancestors. This is the idea to prove this part here. Okay, so suppose that this is finite, what happens? Suppose that I want to define if I have an edge ij, will be adding the graph at time 0. So what I'm going to do, I'm going to look at the first generation of ancestors, the second generation of ancestors, and so on. Since these generations, I know that this edge has a finite number of ancestors, I know that in some time, I don't need to look at the past anymore. Since I don't need to look at the past anymore, I just run my process, and then I can guarantee that at time 0, I have just the invariant measure of the process. This is a technique that we call perfect sampling or perfect simulation algorithm. So this is the technique that we use because clan of ancestors is very powerful because we can construct the perfect simulation algorithm just going back to the time until a point that we don't need to look anymore to the past, and then we just run the chain, and then we can guarantee that at time 0 we are sampling, we are in the invariant measure of the process. That's just the infinite Gibbs measure that we are interested in. So this is the idea behind of this technique, just to put things together. So now we can understand what we have here. So this alpha function comes because of this branching process that I used to dominate the clan of ancestors. So when I have for a parameter beta this condition here, I know that all the vertices in the graph has a finite number of ancestors. So I can write a perfect sampling algorithm, and then I can guarantee the uniqueness of my measure because I can sample from it. So it exists and it is unique. Well, okay. to define it, to prove this other part here that's concentrated, we also use a dominate process. That's just, let me just come back. So the Markov process that I define is like this. To have an edge in the graph, it tried to be born, but I only add it in the graph with this probability. So we are going to dominate this process, but just removing this item 2 here. So every time that the edge would like to be added in the graph, it will be in the graph. So this new process will dominate the process that we are interested in. So it's simple to do this with this dominating process. And then we can prove that for this dominating process, all the vertices have finite degree. So the same thing holds for our measure. All right, so just to finish, I just want to add some more remarks and comments about both of the works that I present today, because I just take a small piece of these works to present here today. So actually, in this work here from Pablo Ferrari and Anatoly, what they have is that V is more general than in my case, because V is containing RD, in RD. In our case, V is a subset of Z2. I know this is always a good question. I don't know why we restrict to Z2. You know, when you just start doing things and then you don't realize that maybe you can do some kind of generalization. So we just do it for Z2. The second point here, that in this paper, the authors also consider that V it can be sampled from a homogeneous Poisson process. We didn't analyze in this case, but I think it's a nice point. So maybe future investigations. And also in this paper here, the authors were more, how can I say, interesting interpolation results. When you have or when you don't have an infinite cluster in the graph. We are not interested in this kind of these results. Actually, we spent a lot of time in this paper just proving and construct the construction that I try to explain today. And also what we have here is in this paper here, we consider more functions f that satisfies the conditions that I have presented before. And in this paper, they only consider the function f that depends on the phi function that just counts the degrees. So here it's kind of more general. We also have exponential mixing for this measure. As I said, a perfect sampling algorithm that I didn't bring today. But what I think it's something that I should look at is some percolation results for more general functions. I think here there's room for improvement. I think there's some interesting questions that we can think for more general functions. So that's all for today. Thank you.
Okay, thanks, Andressa. Questions or comment? Just please activate your microphone or in the chat.
I will go. I had this question on. So this alpha beta is a sufficient condition, no? So alpha beta smaller than 1 is a sufficient condition. So I suppose this function is monotone, no? It's either increasing or decreasing. So the quarter you are, the easier it is. But is it necessary also? So is it you have existence and uniqueness only on this case? I mean, uniqueness only on this case? Or is the...
That's a good question. Yeah, I don't know what happened when beta is smaller than beta star. Because here we can control, we can guarantee that the clan of ancestors is finite, right?
Yes.
But I'm not sure. I think, yeah, probably it's not a necessary condition. Probably it's not. But I don't know how to prove or what kind of techniques we can use in a different regime.
But you expect somehow that there's still this type of phase transition where you Like you don't have, let's say, uniqueness anymore, or you start having at least infinite range edges?
That's a good question. I will actually Anatoly asked me made the same question a few weeks ago. I don't know exactly if we have a phase transition here, or for example, the question that Anatoly made to me was like, are there some kind of function where we don't have uniqueness of this measure? I don't know, because here I'm look at just well-behaved functions, right? Just because I can control everything. But I don't know what happens when we consider different functions. Then in that case, maybe we have a phase transition that we don't have uniqueness anymore. We don't have convergence to a infinite measure. I don't know.
Because what happens for the simplest case, I mean, when you don't have that function and you just have, you're just penalizing the distances, no? Do you know what happens if?
When we are just penalizing the distance?
Just with when FB is equal to 0, for example. This is also
we can think that M is 0, right?
Yes.
For example, is a lower bound. And then we are going to have the same condition here, but here will be minus beta when we use the clan of ancestors.
But you don't know, like, all of these questions. It's not simpler. Let's say erasing FB is not simpler.
No, I don't think it's simpler, no.
Just last question, sorry. Is it how strong it is with when you change the L1 metric to the L2 metric, let's say?
Good question. Let me see what will happen. Probably the only thing that will change is the form of this alpha. I didn't try to see how different it will be. Let me think. Because the only important thing yeah, I think, I don't know what happened, but I can imagine that what will change, whoops, other side. What will change is this function here, because this function comes from some kind of sum that I do for all the possible neighbors for the edges, and then I have this function here. So I think that it will change, but I never tried to write it down to see if it's better or not, what we have. But yeah, I never thought about this.
Thank you.
Thank you.
But
the construction, just one thing, the construction is the same. Doesn't matter the distance, right? Because here, the rate that I'm going to use for the Poisson process depends on this distance, right? So we can do the same construction, we can do the same thing, all the same steps. The only thing that will change is to guarantee that the clan of ancestors is finite using this distance. But I mean, the technique is the same, it's totally the same. All the steps will be the same.
Thank you.
Okay. Another question?
Good question. Yes.
Yeah.
To go first? I don't know. No? Okay. So I wanted to ask you if you have any. I wanted to ask you first about the exponential mixing, but you said already that you have something like this of the mu measure. So then I wanted to ask you, what about the convergence of the finite dimensional measure somehow, or the finite measure to the infinite volume one? Finite volume measure to the infinite volume one. Do you have any speed of convergence or stuff like that?
Yeah, we have some results comparing both measures, and let me try to remember the results. But it's clear that when you make n goes to infinity, like for example, the number of vertices, you can see that they are being closer to each other. These measures, when I compare me V with me, using some inequalities that I have. I don't remember now all the inequalities, but actually the convergence is exponentially fast.
Okay.
So yeah, and yeah, this is something good from the clone of ancestors. They also have some kind of similar results for loss networks, because of the technique. So it's
Okay. I know. Okay, that's what I wanted to ask. Yeah. So, thanks.
okay. Thank you.
Okay. Another question, the last one. No? Well, I have a simple question. What about larger dimensions? I mean, you did all the result in Z2. There is a limitation about larger dimensions?
I don't think so. I think as the other question, I think the only thing that it will change, and we need to see what happens is with this function that will change. But I think it's possible to make all the computations, because again, the only thing that we have here is just these rates depend on the length. So in high dimension, we just define a different distance between vertices, and then we can have the same kind of result. Actually, from these papers, they used RD. So in RD, we know that it's possible to prove the existence and other results for this measure. So I think that here it's also possible to do in higher dimensions, but as I said, I don't know why I didn't. You just start with the two, okay, let's see what happened and play with this stuff. And then we just, okay, that's done. And we didn't try it more.
Okay, thanks.
Thank you.
Okay, let's thanks again, Andressa. Turn on your microphone, please. Hey, thanks,
you.
Andressa, for coming.
Thank you.
Gracias.
Gracias.
Gracias.